spectroscopy of molecules in an astrophysical context. Now, he's back in the Philippines after finishing his PhD studies and is currently teaching undergraduate physics courses in UP Cebu. He's also running a YouTube channel, To Slob Physics, which is about basic physics. Right? So, Sir Xavier, how are you doing this fine evening?
Hi Daniel, thank you for that introduction. I'm managing. I'm okay.
All right, let's go. So, should we start?
Sure. All right, everyone. I hope you can all hear me and can see my title slide. Um, the title of my talk is Astro-Binignit, and um, my friend James Tunyaka was kind enough to provide a better description, a hodgepodge of astronomy facts everyone must know. So indeed, this will be sort of, you may find it your first impression like a jumble of trivia and knowledge, basic stuff, essentially. So you may know these stuff already, but I hope you can still appreciate these things which I'm gonna serve you. So by the way, benignit is a dessert, um, merienda. So it's a snack item we have in common here in the Visayas region. We also have versions of this in Luzon and definitely in Mindanao as well. So this dish is like a sweet dish. It's a dessert. It's sweet. Then it has banana, yams, taro, and all stuff that you can you can think of that are sweet. And so I thought that um, this really describes the talk that you're gonna hear tonight. So this snack, I'm still talking about the snack binignit. So this is usually consumed during the Christian Holy Week, and for now for Astro Week, we're gonna have Astro Binignit, right? And um, yeah, this will be the stuff that I'm gonna talk about tonight. So again, you may find these you may find these topics a bit I don't know, maybe trivial even for you. And I learned that we have astronomy students, physics graduates from the audience. So but yeah, just sit back, relax, and enjoy your benignit as I guide you through this talk. So we start with the topic about the roundness of the earth, or yes, the earth is round. So um actually, it was already proven two 2,000 years ago that it is really round. But the current events that arise lately um, bring a concern to the scientific community. So I thought of including this in my talk, sort of to remind ourselves what what things can we observe that prove us, that convince us that the Earth is indeed a spherical um, object. Okay, so the first evidence that we can observe that proves this point is during the phenomenon of eclipses, and specifically the lunar eclipse. So here in this figure, oops, so you can see the moon in different stages of the eclipse. Then you can sort of make out the curved shape of the shadow. And so that would imply if if your shadow is curved, then most likely the object that casts that shadow has a curvature. And if not, otherwise, if it is, for example, if it is flat, and as we know, uh, the Earth rotates, so a flat disk will orient itself. Sometimes you can see it edge on. So during eclipses, for instance, you might see this kind of shadow, but it has not been observed ever since. So yeah, that's one proof that, and the Earth is definitely round, or likely round for the meantime. Another one is dates back to um, centuries ago, um, where this observation of structures casting different lengths of shadows at a particular moment in time of the day. So in this case, we have two sticks erected on the ground. Then, as you can see, it conforms to the curvature of the surface. This can be explained by this geometry. So when you're the sun when the sun is quite too far from the Earth, so its sun rays can be essentially thought of as parallel rays already, and it makes and it allows it enables shadows to be cast by these objects. And as you can see from this demonstration, one stick doesn't cast any shadow, while the other casts a shadow at the same time at noon, for instance. So in this manner, you can sort of infer that ah um, if if different objects at different places cast different lengths of shadows at a particular time of day, then I can measure the length of that shadow, and the angle it makes with a vertical. So this angle here. And then one more thing, I can also measure the distance from that first structure, from that stick to the other one, and make out a semicircle, which enables me to calculate for the circumference of the Earth should it be a round object. And indeed, it was proven by some guy that he managed to calculate the circumference of the Earth to a decent agreement to the present measurement. So yeah, that's the second proof: different shadows at similar times. So this brings me first to the trivia. First trivia. So here's trivia one for tonight. There will be plenty of trivias for this episode because I wanted this to be a bit light to the appetite. So the trivia number one: the first person known to have calculated the circumference of the Earth was. Okay, so forget to submit your answers through the Google form provided by our crew in the chat box. Okay, so I'll continue. One other thing that has been a common observation of travelers in the past, so people before really um, had to travel far, and compared to the convenience of modern technology, it's very hard to locate yourself, especially if you're, for example, you're out in the desert at night. You only have the stars to guide you. So in their travels, these these people, they notice that when they are at a certain point in a certain location, they see some um, formation of patterns in the sky that we call now as constellations. So here are some few examples of these constellations. We will get back to constellations later. Then when they move, before that, this red line, by the way, indicates the local horizon of that observer, of that traveler. So beyond that line, they couldn't see any star anymore. Of course, that's the line of sight here indicated in the broken white lines. So when they travel further, for example, further south, they they start to see other constellations, other formations of stars. While they see, so that's our, by the way, that's our home lizard, which you can hear now. So this lizard here. So as they travel further down, for example, further south, they still see some of these constellations and other constellations starting to appear. So like this, for example, the eagle, shield, and so on and so forth. So the idea here is as they move across the surface of the earth, they see different constellations. And that tells us that because our sky is essentially thought of as a dome, okay? So when we travel across the surface of our earth, so we are also our view, our line of sight is also traveling across the surface of that dome, which is called the celestial sphere. Okay, and so on and so forth, and back there. So one full circle. So that's another proof that the Earth is round. So you don't get this in a flat Earth because in a flat Earth, where you are standing, you'll immediately see what lies over there. Although it's very faint and it's kind of small, the pattern is small, but you will definitely see it there from afar. And as you continue to walk, you will never see any new constellations that arise from the horizon. So another thing, another aspect of a spherical surface of a round Earth is that when you elevate yourself, so for example, you climb a tree, you can see farther. If you stand in the shoulders of giants, you can see farther, right? So if you've climbed a mountain and like compare the view that you see when you're still like midway to the top and in the summit, you'll see more when you're at the top because of this geometry. So let me just go back to the previous slide. Here it was before you climb the tree. Then when you rose up, your local horizon also widened. Okay, so you have a wider horizon now. In the Visayan vernacular, mas lapad na imong pananaw. Okay. Okay, another observation that we can easily see, especially when we're living near the port. So we see that ships apparently sink as they move towards the horizon. And for me, I've seen ships moving sideways, but whenever I get the chance to see a ship like moving away from me, I wait for it to disappear. So this is also This also can be explained by a round Earth. So as you can see from this diagram here, so this orientation of the boat or the ship is represented by this view. So you're looking at the ship directly, and this is what you see um, in the side. And this broken line is the broken line for the line of sight, your line of sight, or that indicates your local horizon where it intersects the sphere or the circle. Then as the boat or the ship moves away, so it goes here, you can see that the ship also becomes smaller and smaller and smaller as it goes farther away. But apart from that, it also sinks down the horizon. That's the difference between a round Earth and a flat Earth. Because for a flat Earth, the ship will just um, continue to become smaller and smaller until it vanishes on the horizon. Vanishes meaning it becomes a point, so towards the vanishing point of your horizon. But this one is different. Before becoming a point, the ship sinks. That's due to the curvature of the Earth. So you can also extend your imagination that as the curvature of that surface, as the curvature of that surface becomes um, greater or smaller. Circle is the curvature is 1. As it becomes more circle, more circly, the farther before that object will sink down the horizon. So until the extreme case is a flat surface where it never sinks but it becomes smaller and smaller. And if the curvature is so great, so I remember now the curvature is if the curvature is so great, then that ship will sink immediately as it moves, even just with a small distance away from you. Okay, so definitely this gives us clues to the shape of the surface of the Earth. And another old one, um, which you are very familiar of. Um, we have heard of this in history books about circumnavigation, where voyages have been um, voyagers have been employed to seek seek riches from other places at the same time moving in one direction so as to prove that you can reach a certain location by just moving in one direction. So in this particular example, this voyage was done by moving westward, and they reached the east by moving westward. So that tells us that the Earth is indeed round. So if this was a flat Earth, this is a flat map. But if this is the map, they started from here, and then they just went across the globe, and then went back to where they came from. I just wanted to to show my globe to you. But there we also have a mall here in our place. It's quite a big mall. It's a disc. It's not a sphere. But I I one of the fun things that I do is I walk um just one direction and continue to walk until I arrive at the same spot where I came from. So that's the idea behind this circumnavigation, traveling in one direction to reach where you started. You can also do this in planes. So Amelia Earhart was the familiar um, adventurer who tried to circumnavigate the globe in a plane, but unfortunately, it was a mystery what happened to her. But anyways, so yeah, that's about circumnavigation. And another thing that proves that the Earth is round is that we have other people on the other side of the world right now. Hey, we even have audience here that are from another time zone. Okay, time zones prove that we um, we receive different amounts of sunlight and darkness at different times of day because one we're rotating, and two we're located in a sphere, in a spherical surface. Okay, so there's that saying that it's 5 o'clock somewhere, so I can take a break, even if it's not 5 o'clock in your time zone, but it's definitely 5 o'clock somewhere. So this brings us to the second trivia. So which time zone is the furthest behind? And I give you this basket of bread to enjoy with your binignit, your dessert there. Right. Okay. Which time zone is the furthest behind? So um so the time zone, I'm referring to the time zone, not really the place, but just the time zone. So they celebrate New Year's the 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 last. Okay, another proof that the Earth is definitely round is that we have images taken from space, that shows the curvature of the Earth. Here in this picture, we have an image taken by Samantha Cristoforetti of NASA. In the I mean, she's currently in the ISS orbiting the Earth. And the Apollo missions, they took pictures of the Earth while they were in the moon. And if you've heard um, Adrian's talk last Monday, so it was the first time that we discovered the Earth while we are in the moon, that the Earth is round. Yeah, so we have plenty of images found in the interwebs, which are not fake. And other planets around. So we can observe that our neighboring planets of our solar system, solar neighborhood, are round. So it would be a bit, I don't know, selfish or egotistic for us to think that we live in a flat, flat surface, special shape, and it would be harder for us to explain the current theories in planetary formation, in star formation, which which leads us to think that objects that have self gravity and which are massive enough form spherical entities or spherical bodies. Okay, so it's way easier to think that the Earth is round. And one final important thing, things always drop downward, and that is towards the center of the earth. So what I mean by this is, for instance, if indeed the earth was flat, so if we are in the center and we drop an object, it will definitely fall down because the center of our disk, our flat earth, is down. But as we move towards the edge of our disk, so as we, for example, here, so you can see here from the arrows, these indicate the forces that the person experiences. The force of gravity should be directed towards the center of your disk. And also, um, you can also see that more mass is located here compared to the remaining part here towards the edge. So that means it makes sense that more pull will be experienced by you towards that direction, to the left of me, to the left. Yeah, and as you go further towards the edge, you you there are plenty of simulations showing this very nicely in YouTube. So, but you almost lie down, and until you reach the very end where you can stand sideways, which makes sense because the center is towards that direction. So you can balance yourself in the edge. You won't fall off because there's gravity. Everything that has mass has gravitational attraction with each other, with all other things. So if the Earth is round, so this can be observed plainly in um, different places on Earth. So here in the Philippines, objects move down, fall down. There in India, definitely objects move down. In in the southern part of Africa, in Australia, in Brazil, in Japan, all move down towards the center of the Earth because of that force we call gravity. Okay, yeah. So those are the things that you can think of whenever you're asked by someone to prove to you that the Earth is round. Because sometimes these things can be easily um I don't know, overlooked. Also me, I had to review even because whenever I'm asked, like it's such a surprising question to ask if the Earth is really round. Because flat earthers also have a point though. This is what I mean. Um they um or people who think that the Earth is not round, so whatever shape they want. So they just take evidence like as they see it, and um without interpreting the reason behind that. So for example, I can definitely say that the Earth is not moving and it's the center of the universe because the stars are moving around me. The sun is moving across the sky while I'm not moving. But if I it would be fine if I didn't know about um gravitation, if I didn't know about the orbits of the planets, if I didn't know about stars. So that's what's meant by to interpret what you observe. Okay, so but it's a good reminder for science enthusiasts, for astrophiles to keep this in mind and um to have a educated discussion with other people rather than to bash them. Okay, so let's educate. So moving on. So speaking of gravity, one consequence of gravitational force is uh, tides. Okay, so these tides or tidal forces, because they are essentially forces, they happen due to the force of gravity changing over distance. Because gravitational attraction is an attractive force, but it decreases with distance by 1 over the square of the distance. So in this slide, I show here the Earth. So with covered in water, in ocean. Then there's the moon. Okay. So there is some attraction between the two. So let's just look at the effect of this attraction um, towards the Earth. And I indicate 3 points here, two in the edges and one in the center of the Earth. So because of the gravitational pull of the moon, Earth will be accelerated towards the moon. So Earth will move towards the moon. But because this point is nearer to the moon, then this will experience a greater force. Okay, and then the center will get much force, and then the least force will be for the outer edge. So this is the common explanation that we get um, to explain why we have these so-called tidal bulges. Okay, when we observe that it's the water here, the water level is high, we also observe a secondary high tide. We call it a high tide on the opposite end of your moon Earth axis, and then in the right angle ends are low tides. Although conceptually this has a point, this is much the effects here are much more subtle. Okay, so for this acceleration, for this particular case, we can view this. So right now we're viewing this in the reference point outside of these objects. So when we go to the center of that of this point, so if we go to the center of the Earth, then mark our reference. The one that happened earlier can be thought of as the edges moving away from the center, right? So if I go back to the slides again, so these two dots here move towards the moon, but this dot to the right moves farther because it experiences a greater force and thus a greater acceleration can have, like so. And if we fix the center, so it's like the two edge points are moving away from the center. That is what we call a tidal force. And tidal forces are actually not there. They're fictional, not fictional, but they're fictional. They do not exist. They only exist because our frame of reference, which is the Earth, is accelerating. So in physics, that's called a non-inertial frame of reference. It's the same thing as when you ride a vehicle, move starting from rest, and then it suddenly moves. Then you are taken aback or move back as it accelerates. So it's sort of there's a pushing force that's applied on you. It's a similar thing for the tidal force. These are fictitious forces. Um, but we can also, for us to explain the bulge. By the way, these tidal forces are quite feeble and they are not that strong. Okay, they are 10 million times weaker than the gravitational field of the Earth. So that means definitely the moon's force, which is this tidal force that is brought about by the gravitational gradient. So I'm blurting out words here, but the difference in the gravitational pull of the moon across the Earth, the diameter of the Earth, that gradient produces these tidal forces. These forces are very feeble and are just microscopic, so they cannot definitely um, lift up water, lift up the oceans. And if that's the case, why are lakes not um, also, why don't we have tides on lakes? Why don't we have tides on our cup of juice or coffee in the swimming pool? So there must be another explanation for the bulging of this tides, tidal bulge. And what can help us is to look at other points in our Earth. So instead of looking at the moon Earth axis, we look at the perpendicular axis. So similarly, these 3 points will be pulled towards the moon. Okay, the center will be pulled towards the moon. These two edges will be pulled at an angle. Okay, so sort of like this. Okay, this is the effective shape as earlier, right? I just look at different points and I just label there and the forces that act on them. So if we do the same procedure, so if we fix the center of our Earth, okay, and take a look at what happened, remember that all the Earth was pulled sideways. Okay, and apart from that, the points and the edges are pulled towards the moon at an incline. So effectively, the sideways motion of this point and this point plus a downward motion produces that diagonal force here. So if we draw our tidal force, it's effectively a force that's going downward. Okay, do you see it? Right? So that downward force, that tidal force, plus the motion of the movement of the Earth, plus the pull of the moon of the Earth sideways, creates that force of acted on that point towards the moon. Okay, the resultant force. If we look at different points in our sphere, in our Earth, it actually looks something like this. And as you can see, the tidal forces, which causes tidal acceleration, which moves the things, and for this case, the moves the waters of the ocean. So it squishes the ocean and the poles, and because of that, the equatorial ocean or water in the sides will bulge. It's just like if you have a small fruit, and then you squish it, the sides will burst, right? Or the sides will swell up. So this is the mechanism behind the tidal bulge. So it's not because entirely of that first picture that I showed you, but it is because our Earth is an accelerating frame of reference, and these tidal forces, even though they're very feeble, but because essentially each and every point of the waters of the ocean are um, subjected to this force, to these fictitious forces, because of the moving Earth, because of the accelerating Earth. So they add up to give this scenario or this result, right? Okay. So here comes the sun. We didn't mention the sun earlier, but the sun is there. So when the sun is there and aligned with the moon, The sun, although the sun is a much larger, very much larger thing, and thus is much more massive, but it's quite far from the Earth, so it pulls like half or just one third as much as the moon pulls on the Earth. But their added effect produces um, unusually high tides and low tides. And these tides are called spring tides. Okay, because they spring, sort of a spring, not the season, but they spring forth. So the water comes in, as they say. The tide comes in. And then when the moon moves in its orbit, so there comes geometry where you have a right angle between the sun, moon, and earth um, connection. So you will have not so low tides and not so high tides. And these are called um, oops, these are called neap tides. Neap. And for our trivia number 3, this tide occurs when the moon is either new or full and closest to Earth. Because the orbit of the moon is elliptical, there's this point called the perigee, then the opposite is the apogee. The perigee is where the moon is nearest to the Earth. So that because gravitation again is scales with distance, so the nearer you are, the greater is the gravitational interaction. So the greater will be the pull of the moon on the Earth. So these types of tides can be quite dangerous, especially for coastal areas. So what's the name of that particular tide?
I'd like to remind everyone to answer the trivias because we have a lot of trivias prepared for you tonight.
Yes.
And yeah, if you answer the trivias, you'll have a chance to win 100 pesos. And since we have lots of trivias tonight, you have more chances of winning.
Yes. Thanks, Daniel. Was that you? Okay. So let's continue our journey. So because we're speaking of moon orbits, so the moon can just orbit the Earth and pass in between or at the back of the Earth. But before that, so the before that, this is one important thing I almost forgot. Um, Due to the rotation of the Earth, this bulge is not actually along the Moon Earth axis, but slightly um, at an angle from that axis because of frictional forces. Then the spinning Earth will sort of push the water to that direction of its spinning. By the way, this is possible because currently the Earth spins faster than the Moon rotates or revolves around the Earth. Okay, so that means the land mass, the Earth mass, moves beneath the water, the oceans. Okay, this produces some, um, as I mentioned, frictional forces, and also because of this, the Moon will try to correct the orientation of this. Actually, no, the Moon will not try to correct, but um, it's just because of the friction between the spinning Earth and the waters of our ocean. Okay, that's called tidal friction. Okay, this bulge, because it is off axis, it also sort sort of tugs the moon towards the Earth. Okay, sort of because the moon is not actually tug towards the Earth. Instead, it's given that extra energy to move faster. Okay. So again, the bulge is pulling the moon, is gravitationally attracted to the moon. Okay. And it gives more orbital energy for the moon. And in turn, the moon will speed up. Okay. And to compensate for that, the moon will move into a higher orbit. Just like when you're trying to spin around from an axis, the faster you go, the greater is the force that you feel that you're pushed away from that axis. Okay, so the Earth is, because of these tidal bulges, because of the tides, the Earth is becoming slower each day. But it's, for our lifetimes, it's not very significant. But before, the Earth was spinning, like for a day it can do it in 5 hours compared to the present, which is 24 hours. And someday in the far future, like billions of years, Earth will defend sorry Earth will eventually stop spinning because of the overwhelming friction force has taken its spinning energy, and it will face the moon forever. So that the face will be, there will be only one face of the Earth facing the moon, which is also, by the way, already is facing us in their one face. It is the near side of the moon. Because if we look at the moon, the same tidal forces act on the moon. So the moon is also a bit um, elongated because of the tidal forces. And the Earth will, as the moon spins on its rotational axis, the Earth will try to correct its spinning and stop it from spinning. Like telling the moon, just face your face to me, and I continue to spin. The Earth will eventually stop spinning too because of this. Okay, and that phenomenon is called tidal locking. So the moon is now tidally locked with the Earth. And as I mentioned, that's called the near side of the moon. And then we have nice pictures of the moon here. So the yellow moon is usually when it's near the horizon, where many gas molecules of the atmosphere absorb the light. Then this is when the moon is high up above the sky. Then during lunar eclipse. So yeah, but of course the moon is round, just like the Earth. It has a far side, so the side that we don't usually, we never see, and we will never see. So this photo was taken by the Luna 3 spacecraft of the USSR, of the far side of the moon, and you can compare immediately that the features are quite different than the near side. The near side are full of Maria or mare. So mare is a Latin term for sea, because um, astronomers ages ago um, really thought that these were seas, that there were oceans in the moon in their observations in their telescopes. So that's how the mare or the Maria thing came to be. And also some impressive impact craters. The far side has a different set of features. There are um, many ridges over there, and it is thought to be a much thicker side compared to the near side. And by the way, these mares look dark because they are quite lower in the surface of the moon compared to the craters which appear white. And also the dark coloration are indication of basaltic volcanism or basaltic lava, which is a proof that which is evidence that the moon was very active during the time when it's early in its early formation, um around 4 billion years ago. So brings me to the fourth trivia. What's the largest crater on the moon? Can it be this? This one? So only you know. So answer now. Okay, we continue with our discussion. It's becoming a discussion, sorry. Continue with our talk. Oh, there's another trivia. What a surprise. The fifth trivia. What is the name of the eighth studio album by the English rock band Pink Floyd, which is their most commercially successful album and is among the most critically acclaimed records in history? That is trivia number 5 for you guys. Okay, so this is what I wanted to say earlier. Speaking of orbits, so if the moon can be in line with the sun, why doesn't the moon cover the sunlight every time? It passes in front of the sun. And why doesn't the moon be covered by the shadow of the earth every time as well? So that can be explained due to the tilt of the moon's orbit relative to the so-called ecliptic. So I'll just define terms first. Ecliptic is the plane of the orbit of the earth relative to the sun. And because that's the best. I mean, that's I will not say the best, but that's one of the reference planes that we can define that is easily identifiable. So the moon is tilted 5 degrees from the ecliptic. And as you can see from this diagram, there will only be occasions where the moon will cross the plane of the ecliptic, and that's called the node. So this line here connecting the earth, moon and the sun, if the moon if the moon's orbit happens to pass through that node, there will be an eclipse that will happen. Okay, solar eclipse when the moon is in between the earth and the sun, lunar eclipse when the moon is behind the earth's shadow. So in other cases, because again the moon's orbit is tilted, the moon can be too high or too low relative to that node that I mentioned, that line connecting the sun and the earth and the moon. Right? Okay. Okay, we go now to the next topic. I hope I still have some time. About seasons. Again, these are basic stuff. I just like to remind everyone, the audience, about these stuff that are also quite interesting, at least for me. So here in the Philippines, so we don't have 4 seasons. We call our seasons wet and dry. That's because of the rain. That's representative of the rainfall that we receive. So seasons are caused by changes in sunlight concentration over an area. Okay. So because the Earth is round, there's another proof that the Earth is round. Uh, This time I'll use my globe. So because the Earth is round and For example, the sun is there illuminating the earth. So those parallel rays from the sun um, do not give the same concentration, or do not hit the land area of the earth the same concentration as it hits in the equator, compared to when it hits the northern part or the southern part. Okay, here in a particular square of area, there will be fewer light rays that hit that area, and thus you will feel cooler compared to here in the equator region, where you have direct hit from the sun. So that alone will tell us that different areas of the sphere will receive different amounts of solar energy. That can be quantified um, as the solar flux, or the flow of solar rays. But that alone can't explain why there are seasons. Because if you see, if the sun is in the side, directly at the side, this and the earth continues to move without a tilt in its axis. So each region in the latitude will be of the same will will be the same zone, for instance. Like it will have the same temperature each time. Of course, I'm not taking into consideration the wind patterns and all other stuff that affect weather, because it's quite a complicated matter. But it will essentially stay the same all throughout the year, okay, as it moves around the sun. But when you have the tilt, which is, by the way, 23 and 1/2 degrees relative to the um, to this vertical axis perpendicular to the ecliptic. So different different orientations of that axis, and at different points of the Earth's revolution around the sun, will give different opportunities for land areas to receive sunlight. Okay, if you are near the equator, there is not much difference, but this is quite significant as you go farther towards the poles. And the extreme case are the poles. If we look at the poles, so right now we're in September. Oh no, in October, nearing November. I lost track of the months. So as the Earth spins, so that region in the northern North Pole receives um, more or less constant amount of sunlight. Okay, by so much. Then as it moves in its orbit, so as you can see, because this tilt is more or less constant, 23 and 1/2 degrees from the vertical. So as you can see here, as the Earth rotates, the northern region for that whole duration will stay on that dark side, okay, unlit side of the Earth. And as it moves, it again receives a different amount of radiation from the sun. And finally, after 6 months, it becomes bright again in the northern region. And the opposite is true for the southern hemisphere, the southern pole. Right? So there are other countries that celebrate their different holiday festivities, and in a different half of the year. So which can be strange if you live in a particular hemisphere. But that explains why. So why there are seasons. It's because of the flux and the tilt. Solar flux and tilt. Okay, I don't know with the organizers if we still have time.
Yes, sir. There's no problem. I think the participants are also uh they also want.
Okay, if you like to continue, just and you can leave if you if you want. But thank you very much for staying. So we'll have a stargazing break. So right now but we're not going out, of course, because here in the Philippines in Cebu it's quite rainy. So I'll just open a program for you to see. So can you see the software that I've opened? Do you see something?
The words are not that clear, sir. Maybe you
Okay.
can share your screen.
Oh yeah. I just yes, I was supposed to share my screen, sorry. Thanks for reminding me. I'll go back to Zoom. Share screen. How about this? It's still not very clear now.
It's clear already, sir.
Okay. So this is a program called Stellarium. And you might be familiar with this already. This is a free program which you can download. You, and in here you can use this as a star chart and just to stargaze in the comforts of your room. Okay, I want to talk about a small um thing about the zodiac. Okay, we're familiar with zodiac signs. So the Western zodiac. So why are they um why are they assigned to those months? Why are they assigned to those particular months? So right now, let's take a look at the particular direction, the east direction. Then I'm gonna wait for a while. Gonna move the time forward until the sun rises. Oop. So what constellation do you see, or what zodiac sign do you see? You're probably answering in the chat, but I can see the chat. Virgo. Yes, you can see Virgo right there. If I move forward, what's next to Virgo? You have Libra, right? Okay. So here's what I'm gonna do. I'm gonna reverse the time first. Oh, right there. And then this one, use this. So I'm gonna move different months and just observe what constellation you see um, rising with the sun in the east. Okay, so let's go to November. This guy right here. Then December, or actually this also, this one. In December, you have another one. Let me reposition this for you. Then in January, I don't know if you can still see that like this. February, March, April, May, June, July, August, September. Back to September or October. October, then November. Okay, so those constellations are called the zodiac constellations. So if you remember what I mentioned about the ecliptic, so the ecliptic is the plane of the Earth's orbit with the sun. So imagine if you are looking directly at the sun as Earth. You're Earth, you're not a human. You're not a human being. You're a planet Earth. So you don't have eyes that will burn if you look at the sun. You just look at the sun. So as you turn, as you spin your axis, as the sun rises from your east side, um, there's a particular constellation that's in directly in its background. Okay, and and it traces all throughout the celestial dome or the celestial sphere. It traces out 12 constellations, which what I just showed you earlier. So that's the sort of reasoning behind the Zodiac. The zodiac signs are different from the zodiac constellations in a sense that the zodiac constellations actually take up irregular spaces in the sky, irregular areas. So, unlike the zodiac signs, which are evenly divided all throughout the year, so that implies that the sun will pass through that pass in front of that constellation like at equal intervals. But the actual constellation are different in size. So they are different in that way, but in a sense what I've shown you are the zodiac constellations. And this is one of the indicators that ancient peoples use to help them with their timing, with their calendars, in timing their harvest, in timing their different festivities. So that is how the constellations arose, and all of these patterns, which sometimes look very strange. I can also show you the artwork. So this is due to the imaginative minds of people, and it's an inherent trait of human beings to find patterns. So hence these patterns that you see. Okay. Um. All right. So I'd like to ask the audience. Do you see? Can you identify stars here? Like, can you trace out patterns using your annotation in Zoom? I will zoom it out first and try to see if you know your constellations or if it's even clear. It's not very clear, right?
It is clear, sir.
Okay, so I'll put it in the current time lang. Oh yeah, this is the current time. Okay, anyone in the audience can trace if you want to can trace something. Anyways, it's I think it's hard. Ah, Cassiopeia, very good. Very good for Cassiopeia. I will do triangulum because I think it's easy. Oops. This one, right? Oh no, that's including Aries. So I'm not very good at this, honestly. But let me just tell you a bit story. When I was young, like in grade school days, I always see the um star cluster, the Perseids, and I always thought that that was the Little Dipper. Then during high school, I have a classmate who was more keen on observing the sky. He pointed out to me the Big Dipper, the asterism Big Dipper, and from then on, I sort of got the context that these constellations are this big. They are quite large in the sky. So if you haven't already, try it whenever your skies are clear over there. Just try to look up and find the known constellations, or you can also make up your own if you like and make your own catalog. Anyways, that was for the break. Let's go back to our talk. This will be quick now because we're running out of time. And there's a heart even stop share. I will stop share. So thank you for the participants. All right, we're done with our stargazing break, and this brings me to the next trivia and the final trivia for the night, which is the 13th constellation of the zodiac, also known as the Serpent Bearer. If you didn't notice, so there was one quite large constellation over there that's also part of the zodiac constellations, but it's not part of the zodiac signs. Although it's been in the news lately that it will be added, but it will not be very convenient for the horoscope aficionados because their signs will be changed, might be changed. So which constellation of the zodiac is this? What's the name? That's the final trivia for the night. Remember to to answer in the form. Okay. All right. Oh wait, I didn't show the. So this is the question. Which is the 13th constellation of the zodiac, also known as the Serpent Bearer? Okay, so that was for that part of the talk. Um, if it's okay, I would I don't know if what the audience would like. If you would like to ask some questions already, I can also do that because I already way past the time.
Hi, sir. Would you be okay to answer a couple of questions?
Yes. So
Right.
maybe we'll just
So,
stop there.
right. So, I'd like to ask people from the audience. Um, I have a question from Adrian Bayani. Can you please ask your question, please?
Okay. Hello po.
Hello.
Narinig niyo po ako?
Yes. Dinig na.
Okay. Yung question ko po is, bakit po color red ang moon kapag lunar eclipse?
Okay. And that's a nice observation. Thank you for your question. Was it Adrian?
Apo.
So let me show you the picture there, but I'll show you the other one. So before before the full eclipse, you see the shadow is is normal, what we expect, dark. But in the full eclipse, it becomes red. So that is because of the diffusion of the sunlight as it passes through the atmosphere of the Earth. So it's it's more or less a similar idea to how sunsets are red. Okay, as the sunlight passes through thicker gas or thicker atmosphere, so part of the light is taken out, and what's left is the red part. So this part here, I will show you the diagram for the eclipse very quickly. No, here. So so the shadow of the earth has two parts. You have the umbra and the penumbra. So the umbra is this darker one, and then the penumbra is this sort of fainter, sort of more diffuse part of the shadow. So the umbra part is essentially light is not there's not much light in there, but as you can see in this edge of the earth, this edge where the light grazes through the atmosphere, actually part of it will also hit the moon, and that causes the red coloration in the in the supposed lunar eclipse that we see. It's due to the fact that the sunlight grazes the edge of the atmosphere, and part of the light is taken out, and what remains is the red part of the sunlight.
All right, I hope that answers your question. Before we proceed to the next question, can I ask everyone to please turn on your cameras so we have a more interactive feeling? Yeah, thank you. Thank you. Okay. So, are you okay if we answer a few more questions there?
Yes, please.
Okay. So, our next question would be from Clarence Mucho. I'd like to ask you to unmute and ask your question. Thank you.
Good evening, sir.
May gabi. Good evening.
Um, I just want to confirm if my guess is correct. Why is that in some point in Earth is that the gravity in some point in Earth is not the same, as we all assume that the gravity is the same in all areas in the Earth.
Okay, so that was your question.
Yeah,
Okay,
that's my question, sir.
yes. So gravitational attraction is dependent on the masses involved. Okay, and the Earth itself, if it were a uniform sphere, then the gravitational acceleration, or essentially the gravitational force in the surface of the Earth, will be constant. Okay, if it were the same density inside the Earth. And as we know, that's not the case. So there are parts of the Earth that's more dense. So there are different minerals in some regions, and also the elevation of someone, or the elevation from the surface of the Earth, or or sea level, will also affect the strength of the gravitational field. Okay, because as you go farther away from the center of the Earth, then the gravitational force will weaken. So there are many things that can cause a difference in the gravitational acceleration of a particular place. So that was one, the density of the region. So in fact, um, there are instruments so-called gravimeters, which measure the gravitational acceleration of a particular location, and industries use this to look for oil or um, mineral deposits underground. Okay, because the denser the material, the more mass is there. So therefore, gravity is much stronger over that region. So that one, and then the other one is elevation. Okay, your elevation from the sea level or the surface of the earth. And another one, which may be quite subtle, is due to the rotational bulge. This is different from the tidal bulge of the earth. So the earth, because it spins, so the equatorial regions also bulge out compared to the polar regions. Yeah, I'm speaking about the landmass this time, not the oceans, but the landmass itself. So that would mean that people from the poles are much closer to the center of the earth compared to the people in the equatorial regions. Okay, so um, you would um, you would weigh different in the North Pole compared when you are in the equatorial region.
Okay, thank you, sir.
Thank
No
you. That was
problem.
sorry, that was David, right? Sorry, David. I
Thanks,
called
David.
you Clarence. So our next question will be from Clarence. So you may now ask your question, Clarence.
Hello, sir.
Hello.
Um, Out of curiosity lang kasi, sir.
Mm.
Um, um, we know that the spinning of the Earth affects the movements of the winds,
Mm.
especially. Di ba we call this as Coriolis effect?
Mm.
So we talk about the spinning of the Earth and the phenomena of uh, lunar tides that
Mm-hmm.
was caused by gravitational pull or gravitational field of the Earth. So,
Mm-hmm.
kinonect ko lang ho kasi, sir.
Mm.
Does gravitational field of the Earth contributes to the changes in Earth's climate? Kumbaga sa weather
Mm.
na nararanasan natin.
All right. Um, that's a good question and quite hard for me to answer. Because it's the effect of gravity on weather patterns. I couldn't connect them directly, at least in my mind right now. Um, Gravity can definitely affect um, um, tidal tidal behavior, and maybe tides also can affect how some weather patterns occur. I'm not so sure, but that's the only thing I can figure out right now. I couldn't find any direct connection with gravitational um, forces with weather.
Sir,
It's more
can I
of
have a
a
follow-up kasi?
okay. It's more of a thermodynamic effect.
Um, and speaking of, ngayon ho kasi ang ng issue ng climate change.
Mm,
So, nano-notice ko yung depletion of ozone layer nag-o-occur lang sa Arctic
mm,
Circle.
mm.
So, does gravitational field affect this? Kumbaga
Ah,
may
okay.
ano ba?
I think it's more because of the um it's more of the wind patterns themselves that that explains why the large ozone is in the poles. Not much as because it's in the poles and it's where the um rotational axis is. I would think that it's more of an effect of the wind patterns themselves, not the gravitation.
Thank you po, sir.
All right. Thank you, Clarence. Are you okay to answer a few more questions, sir?
Yes, we can go on and on
Okay. So we have a question here from
if
JP.
people are still.
He is asking, why does the moon appear larger early in the evening than later at night?
So that's a nice observation because I always wonder about that whenever I see, and it's quite a beautiful sight to behold. Um, one explanation I can share to you is it's an optical illusion because the moon is already you if it's in the horizon, you can compare it with other things in the horizon. For example, buildings, mountain tops, or even trees. But when it's high up, so it's just there. Maybe there's a plane passing by or some stars. So I would say that it's an optical illusion effect that that makes the moon appear brighter. But if you have a telescope, then try to measure the angular diameter of the moon when it's in the horizon. Maybe that's a good exercise. And then measure it, or maybe just use a coin. Because I don't know if you extend your hand with a coin in your fingers and sort of cover the moon with that coin while it's in the horizon and up above the sky. So try to see if they're actually similar in diameter.
All right. Thank you, sir. We have a question from Znep. Znep, you can now ask your question. Thank you.
Hi sir, good evening.
May gabi.
Akong question day sir kay since a lot of people are into horoscopes bitaw.
Hmm.
How are horoscopes made and do you believe in them?
How are horoscopes made?
Yeah.
Um, so it's just my what I know. So they come a long way. So before astronomy, there was this thing called astrology, and it came into being um, because people looked up to the sky and saw some patterns. So as I mentioned earlier, um, people use stars to chart where they are and what time do they do their celebration, what time of year do they plant their seeds, and until they found some patterns more than just timekeeping or like navigating, like they already consult the stars or they consult on the alignment of planets whenever they want to marry or bear a child and other not so trivial things. So um yeah, it goes way before modern science has emerged. So it's has been rooted in our culture. And currently horoscopes, I think they're made by um palm readers, maybe fortune tellers even. But I do not believe in them. I don't consult in horoscopes. I'm sorry. But they're a fun read if you like to enjoy reading about your supposed future. But definitely the future can't be found in the stars, can be found in the ground.
Okay, Znep, I hope that answers your question. We have one last question, sir, from
Mm.
Ayo Kalika. He is asking if do you have any knowledge on like the early Filipinos have any knowledge on astronomy before the
Yeah.
Spaniards came?
Yeah, thank you for the question. Because I also wondered about that as a Filipino. Um, so it's a bit unfortunate that our records were were not were not are not are not anymore available. I don't know how to say this, but we don't have good records of the past. At least from the pre-colonial era. Other than terms, there are terms that we use, the Filipino folk use to describe things in the sky. So I think there was a Facebook page that researches on this. You might, I forget the name, but um, they um, they describe the legends that are based from the stars and all other stuff related to what you can say as early astronomy. But that's all I can say about that, because there we don't really have a very good record of our astronomy and in general science advancement before the Spanish came to our country. But yeah, regardless, although it gives us a nice feeling that yeah, we had a contribution before or stuff like that, it gives us pride, Filipino pride. But I think studying astronomy or physics or science in general doesn't current studying it now doesn't take away the fun, and doesn't take away the fun of doing this, even if we you don't have a history to look back to. You just make your own history in the present, make your own path. I mean,
All right, thank you, sir. And before we end, I hope can I ask everyone to turn on your cameras so you can take a picture, and then we can post it on our page, and you can look at your faces there, and hopefully you are good looking. I'm not saying you're handsome, okay, or beautiful. Just all right. So um, thank you. All right. So I'll ask someone.
So guys, before leaving, let's have a pictorial first. I'll start with the first panel. So 3, 2, 1, say cheese. Okay, that's it for the first panel. Second, 3, 2, 1, say cheese. Then panel number 3. 3, 2, 1, say cheese. Then okay, that will be it. Thank you so much, guys.
All right. So I'm sure not everyone knows which panel you belong to. So we were all smiling all throughout that one. So thank you everyone, and I'm very happy that this talk has been very engaging, especially in the chat. Yeah, I can see some answers there. That 13 is a not so good number. Right. So unfortunately, we have reached the end of today's webinar. Is there anything else you would like to say, sir, before we go?
I'd like to thank the organizers, Fizoc, Astrosoc, and the physics department of the University of San Carlos for inviting me to this very humbling opportunity to share my thoughts with the Filipino people and other even other nationalities. Thank you very much for your time and for listening, and I hope um, you pass it on to others what you've learned something today and share to them the wonders of science and astronomy.
All right. Thank you very much, Sir Xavier, for such a very interesting presentation. Tomorrow
Thanks.
morning at 10 p.m., we will be joined by another speaker. Make sure to check out the USC Physics and Astronomy FB page and register if you have not already. If you cannot register anymore, do not worry. This webinar is also live streamed in our FB page as well. We encourage everyone to fill out the participants' feedback form. The link is posted in the Zoom chat box, the Facebook live stream comment section. Hearing from you guys is highly appreciated so that we can make more and better content in the future. Before we go, I would like to. No, actually, I have already done that. Sorry.